Daddy's looking like a wreck this morning, Maxwell. Alrighty, good morning, gang. Welcome back. So let me get myself together here. It's been quite a morning, file sticker household. I guess I want to begin by apologizing. I definitely did not have you guys' tests finished last Thursday by the end of the day. It ended up taking me all of the weekend and most of last night and some of, I guess, no, you guys were done over the weekend. So they are done. They were done, I think, for your section by either Saturday or Sunday night. So all of those are in, whether you took the makeup or took it with the rest of the class, and whether you took it at the testing center or took it online, all 4 sets are graded. There were a few hiccups, a handful of little issues, but I think most of them have been resolved. Definitely please take a look at the comments that I left, both on the test itself and on your written work. So the reason this grading process takes so long is because I take the time to go in and mark up every little thing. If you make a mistake, I show you what the mistake was, how to fix it, all of that stuff. So please, please, please take the time to look at the comments that I left on your work. That's how you improve, right? You need feedback, and we need to respond to that feedback in a meaningful way, you know, by patching up our skills or whatever it is, you know, practicing a little bit more with whatever it is that you got wrong. But yeah, that's it. The tests are graded. Everything's in. If you want to talk about anything test related, you can come to see me in office hours. Be happy to do that with you, or you can send me a Canvas message or a DM on Discord, any of that stuff. Let me get the document camera rolling and we can get started for the day. Come on. Oh, no, doesn't see the doc cam yet. Okay, try again. Let's see. Oh, I think this is the first meeting, first class in the new space too. So you guys may or may not notice that I'm coming to you from a different room here in the Shea file sticker. We've moved my office setup back to the spare bedroom where my mother stayed with us to help with the baby for a little bit, in hopes that it would mean you guys hear less of the puppy, less of the baby, and give you a slightly more focused environment. Obviously, you see the puppy behind me right now, but if he starts making noise, we have the option to put him somewhere far away through at least 2 doors, so you won't hear as much of that. So I hope that improves your experience. All right, let's do the thing. Close this up. Okay. So this, of course, is MAC1140, section number 008, which means we're talking pre-calc. And today is the 5th of October, 2021. Remind me, have we gotten to actually talk about dividing polynomials yet? I don't think we have. I think I kind of introduced it last Thursday, but we haven't really looked at the synthetic division, long division, factor theorem, remainder theorem, that sort of stuff, right? Let's see where I've got your group and the homework. If memory serves, your group is ready to start talking in depth about dividing polynomials and how we use division algorithms to factor. I think that is the case. So 3.3, I posted for you guys just, oh no, has 3.3 been up for one? No, I just posted that for you guys yesterday. Okay, yep, so today we're moving on to section 3.3. Which is a fun section. This is cool. So over the next couple sections, 3.3, 3.4, and 3.5, I will be sharing with you guys kind of all of the standard high order tools for factoring polynomials and graphing polynomials that people do when they want to do this stuff by hand. It's very important for building intuition, helping understand how functions in general work, especially once you get to Calc 2 and talk about power series. You'll start to see these really neat connections between polynomials and other functions. But for us, what we're trying to do is just get comfortable with the mechanics, the basic rules and definitions, what these things mean, and how to play with them. So the primary thing, remember polynomials are like, and I think I've said this before, the function version of whole numbers, right? And in that same way that we can divide whole numbers nicely, we can divide, we can divide polynomials nicely. Oh, I'm sorry, give me just 1 second. Okay, sorry about that. Just wanted to get things together. So polynomials are like the function version of whole numbers, right? And what I mean by that, specifically with respect to division, remember in 2nd grade or whatever, when you were first learning how to divide numbers, if you were told to divide like 11 by 2, you would say, oh, okay, how many times does 2 go into 11? It goes in 5 times, but then there's a remainder, right? That doesn't go evenly into 11. There's a remainder of 1. So given integers, whole numbers, P and D, we can find, so my goal here is to take P and divide it by D, like 11 divided by 2. Given 2 integers, P and D, we can find integers Q and R such that when you divide P by D, you get Q, the quotient. So like, if I were to take 10 over 5, that would be 2, or 15 over 3, Q would be 5. But if I try to divide something like 11 by 5, I would get 2 plus this remainder term. So what would we say if we're dividing 11 by 5? We would get 2, but then the remainder there is 1, right? Because 5 times 2 is 10. So 1 more to get to 11. So you can write any 2 numbers as P over D as Q plus some remainder over that same D that you're dividing by. So for example here, 11 divided by 5 is almost 2, right? It's 2 with a remainder of 1. So you'd say 2 plus 1 over 5. And since polynomials have basically the same algebraic structure as the integers, we can do this shit for polynomials also. This is actually a really deep theorem in abstract algebra called the Euclidean algorithm. And any space, any collection of algebraic objects where you can do this is called a Euclidean domain. And if you elect to study algebra at a higher level, Euclidean domains will become very important to you. Something you'll notice here is that the remainder is always smaller than the divisor, right? You can't have a remainder of 5 or greater when you're dividing by 5, because then 5 would go into that number again. Similarly, for polynomials, P of X and D of X, we can find other polynomials. So again, my goal here is to take the polynomial P of X and divide it by the polynomial D of X. We can find other polynomials, Q of X and r of x, which play the same role as the numbers q and r do in the normal number division. So p of x over d of x would be equal to some quotient polynomial. And if d is a factor of p, in other words, if p is cleanly divisible by d, then this would be the whole story. But of course, that's not always true. Not every polynomial is a factor of some other polynomial. So in that case, where the division does not work out cleanly, you have this remainder term. Right? You notice it's exactly the same as the rule for integers, right? So polynomials form a Euclidean domain. That's the upshot. Now here, instead of saying the remainder is always smaller than the divisor, we say that the degree of the remainder is always strictly less than the degree of the divisor. So if the divisor is a degree 3 polynomial, if you're trying to divide some big polynomial by a cubic polynomial, then the largest remainder you could have is a quadratic polynomial. This can also be written in another form. So this is one of the ways, as you learn and work through the homework, dividing polynomials, some of the questions will ask you to state your answer like this. But there's another way to write it that doesn't involve any fractions. And I know you guys love getting rid of fractions. If there's anything I learned grading your tests, it's that we're still not as comfy with fractions as we need to be. And that's a place you can come talk to me in office hours and shit. I would be happy to work with you guys and get you there. I don't want you struggling with that. But there is another way to write this without any fractions. And that comes from multiplying both sides by this denominator, d of x. See, if I multiply every term in this expression by d of x, the left-hand side, the d of x would cancel, you just get p of x. On the right-hand side, q of x times d of x is just that, q of x times d of x. And then here, the d of x would cancel as well, and you just get r of x. So these are the two different ways that you can write the result when you divide one polynomial p by another polynomial d. They're equivalent. So the first few things we're going to do today, we're just going to practice. I give you a polynomial p, a polynomial d. I say divide them and write this shit. You'll see it's not that hard. There's two ways to do it. You can do what's called long division or synthetic division. Synthetic division only works in a special case, but it's kind of the most important special case. So it's what you'll be using probably more often than long division. But we'll start with long division because it's a little easier to understand how it's working. Okay. Let me grab my notes here. We can get some nice examples, because if I just pull these out of my ass, they will not be nice. Okay. Sorry, the flow is not as smooth as it normally is. I'm still kind of figuring out this new workspace. All right. That works. Okay. So let's do it. Let me just show you how to divide a couple polynomials. We'll start with a simple example. I guess we should say there's two ways to do this. Long division and synthetic division. And we'll practice long division first. Okay. So let's take the polynomial, call it p of x. I really do think the easiest way to learn this is just through examples. Let's divide the polynomial p of x equals 6x squared minus 26x plus 12 by the divisor d of x equals x minus 4. Remember, dividing is a lot like factoring, right? When you factor like an x out of an expression, you end up dividing every term in that expression by x. So kind of what we're asking here when we try to divide p by d is this a factor of this? And if not, how close can we come to that? That's essentially what we're asking here. The algorithm to get the job done let's see, state the answer in the form. P over D equals Q plus R over D. Okay, here we go. The long division algorithm for polynomials looks a lot like the long division algorithm for numbers. I'll draw a kind of division symbol. And underneath here goes the thing we're dividing, 6x squared minus 26x plus 12. And over here goes the thing we're dividing by, which is x minus 4. The way we do this is at each step, and it's a looping algorithm, it's a thing we kind of do again and again. And at each step, we just pay attention to the lead term. So here, the lead term is 6x squared. And here, the lead term is x. And I'm going to write something up here. The thing that I write up here in my first loop of the algorithm is whatever it takes to turn this into this. So in other words, I ask, what is 6x squared divided by x? Or equivalently, by what must I multiply x to turn it into 6x squared? So if I want to multiply x by something and turn it into 6x squared, that something has to be 6x, right? Because 6x times x is 6x squared. So I put the 6x up here. Then I take this 6x and I multiply this whole thing by it. I distribute it. So 6x times x is 6x squared. 6x times negative 4 is minus 24x. And then what we do, just like in elementary school, you subtract the bottom from the top. You need to make sure that you subtract the whole bottom from the whole top. So these parentheses are full. 6x squared minus 6x squared is 0. That's by design, and I'm not going to write the 0. Negative 26x minus negative 24x is negative 26x plus 24x, which is negative 2x. And then 12, there's no constant here for me to subtract. 12 minus 0 is 12. Or if you like the way you thought about it in second grade, you just bring down the 12. Right, if there's nothing to subtract from. That was one loop of the division algorithm. So remember what we're doing, there's a question in chat. The question was, where did the minus 24x come from? After we find this 6x, we distribute it over this whole thing and write that answer down here. So 6x times x is 6x squared. 6x times negative 4 is negative 24x. So after we find the 6x, our next step is to multiply this whole thing by 6x, and we write that answer here. Then we subtract that whole thing from this whole thing, and we write that answer down here. And that is, again, one loop of the division algorithm. So we do this again. Paying attention just to the lead term, negative 2x here and x here, I ask, what must I multiply x by in order to turn it into negative 2x? And the answer there is negative 2, right? Negative 2 times x is negative 2x. So I write a minus 2 up here. And then just like before, I'm going to distribute just this -2 to this whole term. So -2 times x is -2x. -2 times -4 is +8. And then I subtract the bottom row from the row above. Very much like what you did in elementary school. -2x minus -2x is -2x plus 2x is 0x. 12 minus 8 is 4. And then there is no polynomial term that I could multiply x by to turn it into 4. So we're done. And that means that this is my quotient, q of x. And this piece down here is my remainder, r of x. So right here is everything we need. Then we just have to see what they wanted. State the result in the form P over D equals Q plus R over D. Well, P and D were given to me. I've just found Q and R. So if I want to state this answer, I would say 6x squared minus 26x plus 12 divided by x minus 4. That's what we're doing. We're dividing that quadratic by x minus 4. That's your P over D is equal to Q, your quotient, 6x minus 2, plus the remainder term, which is R over D, 4 over x minus 4. And that would be your final answer. You guys see how this is in this form and where every piece here came from in this? It's a good moment to stop for questions. What are we thinking?
So would that whole thing that you circled be the entire answer?
Yes, ma'am.
Okay.
Yep, because they said state the result in this form. So the thing on the left here is P over D. It's this. And the thing on the right is Q plus R over D. It's this. So yeah, this whole circled thing there would be our answer. And kind of the idea here is if this remainder was 0, then this term would be 0. So this whole piece wouldn't be here. And we would learn that, you know, when you divide the one polynomial by the other, you just get this thing. And I'll show you in a little bit how that's going to be used to factor polynomials, because this is the big game, right? Remember, let me bring this back on. Remember last week, what we learned is that if you have the polynomial in its fully factored form, if you have your completely factored polynomial, then you can tell what the roots are, the x-intercepts, and you can tell what the local behavior near the roots is from the multiplicities. So that, together with the end behavior, which is very easy to get, is all we need to draw a nice graph. And our goal here in the first half of chapter 3 is just to graph polynomials. Now, last week, when you were graphing those polynomials, I gave them to you in factored form, or I gave polynomials to you that were very easy to factor. But most polynomials are very hard to factor. Remember when we talked about Everest-Galois and how it's, it's impossible to come up with a formula for the roots for degree 5 or higher. Factoring polynomials is very, very hard. So the reason we're learning how to divide polynomials is because it's going to allow us to factor big polynomials. There is no, we don't want to use a cubic formula or a quartic formula. They're horrible. They take several pages. So when you're given a big polynomial and you want to factor it, division is going to turn out to be key. So yeah, I will show you how we will use this to factor polynomials. But first, we need to just get a little bit more practice with it. It's a good question. Other questions about this? Okay, let's try a slightly larger one. Let's divide the polynomial 8x to the 4 plus 6x squared minus 3x plus 1 by the polynomial d of x equals 2x squared minus x plus 2. And write the answer in the form. Let's do the other one. Remember, the other form we can use to state our answers here is P equals Q times D plus R. Same thing. I'm going to write my division symbol. And on the left over here, I write the thing I'm dividing by, d of x, which is 2x squared minus x plus 2. It's up a little bit. Underneath there, I want to write my polynomial p. Now, there's something a little bit weird about the polynomial p. It doesn't appear to have a cubic term, right? We've got 8x to the 4 and then 6x squared. There's no x cubed here. When you're dividing polynomials and they're missing a term like that, like you have a degree 4 polynomial and it doesn't have x to the 4, x cubed, x squared, x and constant, if any of those terms are missing, you need to insert them with a coefficient of 0. Remember when we talked about finding coefficients for things like this, we would say the coefficient of x cubed is 0. That's important here. So I'm going to write this in as 8x to the 4 plus 0x cubed plus 6x squared minus 3x plus 1. Looks like I need a little more space there. Okay. All right, so first kind of big thing to remember, anytime there's a missing term, you need to write it in with a coefficient of 0. This will be especially important with synthetic division, but it's important for long division also to make things line up. Everything else goes exactly the same as it did up here. So I look at the lead term, 8x to the 4, and I look at the lead term, 2x squared. In order to turn 2x squared into 8x to the 4, I would multiply 2x squared by what?
Four x squared.
4x squared.
Yeah, very good, 4x squared. And then I'm going to take this 4x squared and distribute it to every term here. I'll write that answer under here. So 4x squared times 2x squared is 8x to the 4. That was by design. 4x squared times negative x is negative 4x cubed. And you see, if I didn't write the 0x cubed, these wouldn't line up. 4x squared times positive 2 is 8x squared. And then I'm going to take that whole row and subtract it from the row above. 8x to the 4 minus 8x to the 4 is 0. 0x cubed minus negative 4x cubed is 0x cubed plus 4x cubed. So this is positive 4x cubed. We're subtracting a negative. 6x squared minus 8x squared is negative 2x squared. And then the negative 3x and the 1, they just come down because these are both zeros. And that's one loop of this algorithm. So I go again. What must I multiply 2x squared by in order to turn it into 4x cubed?
2x.
2x, yeah, very good. So that's what I put up here, plus 2x. And then I distribute just the 2x to every term here. 2x times 2x squared is 4x cubed. 2x times negative x is negative, oh neat, 2x squared. Yeah, we're going to get some extra stuff here. And then 2x times positive 2 is plus 4x. and I subtract the bottom row from the row above. Here, the first two terms give me 0. 4x cubed minus 4x cubed is 0. Negative 2x squared minus negative 2x squared is negative 2x squared plus 2x squared is also 0. Negative 3x minus 4x is negative 7x, and 1 minus nada is 1. So that's our second loop done. And then again, I look at the lead term here, negative 7x, positive 2x squared. Is there any polynomial term that I can multiply 2x squared by to turn it into negative 7x?
No.
No, right? It would require a negative power of x. So that's how you know you're done. So we're done. We are done. And all we need to do now is write down the answer. I think it's useful to, again, just say, okay, here's my remainder. Here's my quotient. And P and D were given to us. So if I want to write my answer in the form P equals QD plus R, it looks like this. P, which is, I'm going to need more space. Let me put it down here. 8x to the 4 plus 6x squared minus 3x plus 1, P is equal to Q times D. So that's, put these in parentheses, we're multiplying two polynomials. So 4x squared plus 2x times D, 2x squared minus x plus 2, plus my remainder, which is negative 7x plus 1. I think it, oh, yeah, let's see in the chat here. How do we solve the denominator is higher than the numerator? Good question. Yeah, so implicit in this whole division process is that the thing you're dividing by, your d of x, is a smaller degree than the thing you are dividing. So P will always be a larger degree than D. That is a necessary thing in order to do this. So a good question came in chat. It was a DM, so I don't think everybody saw it. The question was, what do I do if this guy is a larger degree than this guy? The answer is nothing. You can't do anything. You can't divide that. Or in other words, the division is kind of already done. There's really nothing we can do.
I have a question.
Yeah.
So if what we're dividing by also has a missing degree, would we do the same thing with the 0?
Yes, I think that would be wise, although maybe not 100% necessary.
Okay.
So I think it's nice because it kind of helps you see all the terms and it makes things line up in here, which is really appealing. But I don't think you would get into trouble if you didn't. You just would have some asymmetry in here. You'd have to be a little more careful. But yeah, anytime you have a missing term, I recommend inserting it with a 0 coefficient. So great questions. Anything else on you guys' mind? Okay, then I'd like to pause for just a second and point out again that if the remainder term were 0, if this weren't here, then what we would have just done is started factoring, right? I would have taken this degree 4 polynomial and factored it into 2 degree 2 polynomials if the remainder were 0. So in the case where the remainder is 0, this is a really powerful tool for factoring. The question is, how do I, given a polynomial P, how do I find another polynomial D such that the remainder, when I divide P by D, will be 0? And the answer to that question is going to come in our next lecture. But this is the right time to introduce a particular theorem. Called the remainder theorem. And this says that that given a polynomial p of x, the value p of c is equal to, so p of c is what you'd get when you plug the number c. Given a polynomial p of x and a number c, the value p of c is equal to the remainder when p of x is divided by the polynomial d of x equals x minus c. This is pretty cool, and it's not obvious at all. So what this tells us is that we can evaluate a polynomial, right? Like if I wanted to plug x equals -7 in here, instead of, raising -7 to the 4, raising it to the 2, and then multiplying all those by those constants and then adding them all up, which is a fairly long process and involves raising, to pretty large powers. Instead of doing all that, I could take this polynomial and divide it by x minus 7. And then whatever I get out for the remainder would be the value of p of c, value of p of 7. Notice that in this theorem, the d of x is a degree 1 polynomial. So the remainder will always be a degree 0 polynomial, which is a constant. So it'll just be a number. This remainder, when you divide p of x by x minus something, just x minus a constant, will always be a number. And that number is the same number you would get if you plugged that constant into the polynomial. Now, a special case of this says if that remainder is 0, then x minus c is a factor. So we'll look at that in just a second. Before I do this, I want to show you how to do some synthetic division, show you an example, and then we'll employ that remainder theorem quickly. So what is synthetic division? In service to explaining this, let me pull this example back up here. Look just at the division algorithm part, this purple here. Notice that if we're very careful about where I put things, like arranging the x squareds together, arranging the x's together, arranging the constants together, if I'm very careful about where I put things, I could actually skip writing all the x's. I could just say, I could write a 6 here and say, I know that that's attached to the x squared because of where it is on the page. Instead of writing minus 26x, I could just write a minus 26 here and say, I know that's the coefficient of x because of where it is on the page. That's what we do with synthetic division. This is a shorthand for long division where we don't write the x's, we don't write the powers of x, but rather infer them from the position of the coefficients on the page. And that might sound like it's really complicated, but it's actually not. It's actually super duper simple. And I think after you see me do this a few times, you'll want to use it all the time. But there's a catch. Here's the catch. The rub for my Shakespearean folks. The rub, the catch, the caveat. Synthetic division only works, or can only be used when d of x, the divisor polynomial, is of the form that shows up in your remainder theorem, d of x equals x minus c. In other words, linear. D of x has to be linear. And if you wanted to divide by like 2x minus 5 or something like that, you could factor out the 2 and then divide just by x minus 5 halves. But synthetic division, which is this dope way of doing long division without writing any x's, much faster, much easier, can only be used to divide polynomials, any polynomial p of x, by a polynomial of the form x minus c. So your divisor, the thing you're dividing by, has to be in this form in order to use synthetic division. Now, one of our examples was like that. So I'm going to go back and rework that first example with synthetic division. Then I'll show you one more example, and then we will see how to use that remainder theorem. Here we go. So same problem we did a minute ago. Not the last one, but the one before. Divide p of x equals 6x squared minus 26x plus 12 by d of x equals x minus 4 using synthetic division. And let's just say here, state q of x and r of x. We don't have to write out the whole p over d equals blah, blah, blah. Let's just say what the quotient remainder are. We'll see that they're the same that we got the other way. Here's how it's done. First, I write the coefficients of p, which are 6, negative 26, and 12, and give yourself enough space that you don't confuse them. Then over here, you write the number c. So remember, this can only be done if you're in the form x minus c, if d of x is in the form x minus c. So here, d of x is in that. It's x minus 4. So over here, I write 4. What would be the root of d of x? And then the notation I like, a little division bar looking thing like this. The first step, you just bring down this first coefficient. Then you multiply this guy and this guy. So 4 times 6 is 24. Multiply these guys and write that answer here, just below the second coefficient. So 4 times 6, positive 24. And then you add those. So if I add negative 26 to positive 24, I get negative 2. That's one loop. Then you multiply this times this and write the answer here. So 4 times negative 2 is negative 8. And we add these. Negative 8 plus 12 is positive 4. The term on the far bottom right will be your remainder. And these guys will be the coefficients of the quotient, q of x. Now, whatever degree your polynomial p is, here it was degree 2, when you divide by a linear polynomial, a degree 1 polynomial, which is the only thing we can do with synthetic division, the degree will go down by 1. So I'm dividing a quadratic by a linear. 2 minus 1 is 1. So my quotient is going to be a linear polynomial. So q of x is the linear polynomial whose coefficients in order are 6 and negative 2. That means it's 6x minus 2. And my remainder, like we said, the degree of the remainder is always smaller than the degree of the divisor. The degree of the divisor is 1, so the degree of the remainder is 0. It's just a constant. It's just the number 4. And if you compare this to what we got last time, the quotient was 6x minus 2, and the remainder was 4. Now, I don't know about you. This is easier, right? It's way less writing. A little bit less thinking, too. And if we wanted to, we could write P over D equals Q plus R over D. Because we know P and D, and we know Q and R. Questions on this example?
How did you get the X again? How did you know you're supposed to put the X there?
So the degree of the quotient will always be 1 less than the degree of P. So I
Okay.
know that this is going to be a linear polynomial, a degree 1 polynomial, and the coefficients always come in order from highest order to lowest order. So a linear polynomial is, ax plus b. So this had to be 6x plus -2 or 6x minus 2.
Gotcha. Thank you.
Yeah, of course. Let's try one more. How's about one more, just some practice with synthetic division. And this time, let's maybe see if we can use it to come up with something useful. Okay, so e.g. use synthetic division and the remainder theorem to find about P of 3, where P of x is the polynomial 2x cubed minus 7x squared plus 5. So first off, synthetic division and the remainder theorem are not the only way to do this. I could just plug 3 in here, right? That's an option. But we want to practice synthetic division, and we want to come to understand the remainder theorem. So let's go ahead and do it. If I want to find P of 3, what, according to the remainder theorem, must I divide P of x by? According to the theorem, P of 3 is equal to, remember what that theorem says, it's the remainder when P of x is divided by what? What is my divisor polynomial here? If I'm looking for
X
P of,
minus 3.
yeah, perfect, x minus 3. So that's what we're going to do. We're going to divide P of x by x minus 3. And since x minus 3 is a linear polynomial, it's polynomial of the form x minus c, I can do synthetic division. There's one thing we should note about P of x before we get started here. Any observations about the polynomial P?
It's missing an X.
Very good. P of x here doesn't have any x term in it. So if I'm going to do some division, I need to insert that missing x term as a plus 0x. This is even more important with synthetic division than it is for long division, because it's very easy to forget, and you'll get a totally wrong answer. Okay, let's do the division. 3 goes here. The coefficients of P go here. Little division symbol like this. Bring down the 2. Multiply the 3 and the 2. That gives me positive 6. Add these up. Negative 7 plus 6 is negative 1. Multiply 3 and negative 1. You get negative 3. Add those up. 0 plus negative 3 is negative 3. Multiply these. You get negative 9. Add 5 to negative 9, you get negative 4. Done. That's all the division done. Here's your remainder. And that's really all we needed for this, right? The remainder is negative 4. So P of 3 is negative 4. Now, just for fun, we can write down the quotient. What would Q of X be here?
2x squared minus 1x minus 3.
Perfect, right? It's going to be quadratic because I'm dividing a cubic by a linear polynomial. And the coefficients in order are always these numbers. So that's 2x squared minus 1x or minus x minus 3. So here is our answer. This is the thing we wanted for this particular problem. But we could also write this down. We could treat this like the other problems where you have to write P over D equals Q plus R over D. But let's not bother with that here. We don't need to. This was just for fun. Maybe also just for fun, let's compute. Let's check our work. We can do that by compute P of 3 manually. Or normally, Normally, if I asked you for P of 3, you would just plug 3 in here, okay. P of 3 should be 2 times 3 cubed minus 7 times 3 squared plus 5. And notice that in this whole synthetic division process, I never had to raise anything to any powers. So it's kind of inherently simpler. It's inherently less work to do this. But we can do this too, right? 3 cubed is 27. This is 2 times 27 minus 7 times 3 squared is 9 plus 5. You see the arithmetic's a little bit harder. 27 times 2 is 54. Minus 7 times 9, I have to think about that one for a minute, 63. And then we add 5. 54 minus 63 is negative 9. Negative 9 plus 5 is negative 4. So thank goodness, math works. And again, this took seconds and never required me to raise anything to a power. This took a little longer, right? It involved some powers. And if this was a larger degree polynomial, like a degree 5 or 6 polynomial, in that process, I would have had to raise 3 to the power 5 or 6. Fuck that noise. I would just do this every time. Questions on this example? Okay, I'm going to remind you of our earlier theorem. previous theorem said the following are equivalent. First, that x equals c is a root of p of x. And then second, this means the same thing as saying p of c equals 0. And this was the same as saying that x minus c is a factor of p of x. Everybody remembers this, right? We had one more statement. It's okay. This is what we need here. If you combine this with the remainder theorem, which says p of c is the remainder when you divide x, p of x by x minus c, we see this really useful result. P of c equals 0 means x minus c is a factor, but p of c is also the remainder when you divide p of x by x minus c. So we see the following thing, that x minus c is a factor of p of x if and only if the remainder when we divide p of x by x minus c is 0. So in other words, synthetic division gives us the ability to check if a certain polynomial of the form x minus c is a factor of the original polynomial p of x. And what's better, because we get the quotient out when we do the division, whether you do it long or synthetic, but we'll do synthetic because it's faster. It tells you not only that x minus c is a factor, it tells you what's left over when you factor x minus c out. This is a big, big deal. Okay. Before I show you, no, fuck it, let's just do it. Let's just do it. So what I'm going to say here is, let's factor this polynomial. Let's factor p of x equals x cubed minus 7x plus 6. And the hint I'm going to use is to try dividing p of x by x minus 1. Right? If you plug 1 into this, you see right away you get 0, right? 1 minus 7 plus 6 is totally 0. So I think that 1 is a root, which means x minus 1 should be a factor. But it's not obvious what you would get when you factor x minus 1 out of this. It's not even at all clear how you could factor x minus 1 out of this. There are some tricks that would work. But in general, it's very, very hard. In general, if this is some other polynomial that just happened to have a root at 1, it's very, very hard. So I want to factor this thing all the way down into a product of linear factors. I want the complete factored form. I want something like what you guys were using in your homework last week when you graphed. We're going to follow the hint. We're going to divide by x minus 1. Now the tricky part, one of the tricky parts of factoring polynomials is coming up with this thing. I'll give you a theorem next time that shows you how you can come up with some stuff like this that you can test. But for now, we follow the hint. Remember, since we're going to do some division of polynomials, I need to insert any missing terms here. So I'm going to treat this as x cubed plus 0x squared minus 7x plus 6. And we're going to do the division. So we'll do the synthetic division. So I'll put 1 here, and then the coefficients of p here, which are 1, 0, minus 7, positive 6. Bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 7 plus 1 is negative 6. 1 times negative 6 is negative 6. Negative 6 plus 6 is 0. So the remainder is 0. Which means x minus 1 is a factor of p of x. And that information on its own wouldn't be super helpful. But also we get the quotient. Q of x here is 1x squared plus 1x minus 6. So now let me write P equals Q times D plus R. So we're going to write the result in the form, in that second form. P equals Q times D plus R. R is 0. So P of x is x cubed minus 7x plus 6. Q of x is x squared plus x minus 6. D of x is x minus 1, and R is 0. And the fact that this piece is 0 means I'm really just looking at this. It's x squared plus x minus 6 times x minus 1. And wouldn't you agree that that's a nice first step on the way to factoring this thing? Right? Look, I've extracted a factor. I've extracted a nice linear factor. And also what's left over is quadratic. I know how to factor quadratics, so I can keep going. Without any more synthetic division bullshit, I can just keep going by factoring this using the AC method, using the tools that we know from, middle school. How do you factor x squared plus x minus 6? Well, I need to find two numbers that multiply to negative 6 and add up to positive 1. That's x plus 3 times x minus 2. And then the x minus 1 comes along for the ride. And look at that. I just factored this cubic, this degree 3 polynomial. And it wasn't that hard. I did some synthetic division. I got then a linear polynomial times a quadratic polynomial. And I factored the quadratic polynomial using the tricks that we knew from before. This is what we're going to be doing, for a little while. I'm going to show you a bunch of ways to come up with things like this to try. And then you'll do some synthetic division. If you get a remainder of 0, you learn that that thing is a factor, and you also learn what the other piece is, the quotient. Then you write down this result. You write the result of the division in the form QD plus R. Since R will be 0, you just have Q times D. And then you continue trying to factor Q, whatever that quotient polynomial is. If you're lucky, it'll be a quadratic, which you know how to factor. If you're unlucky, it'll be a quadratic you don't know how to factor, or some other higher degree polynomial that we have to then continue this process on. But either way, this gets us through the door, it gets us started. It allows us to extract one factor at a time from even potentially very, very big polynomials. All right, let me check the time. Questions on this? Zero minus one is indeed -1. Where do we have a 0 minus 1? So I've got two really good questions coming in the chat. The first, I'd like to address the first one first. So isn't 0 minus 1 -1? Yes, it absolutely is. But I don't think there's anywhere we wrote 0 minus 1. And then Victoria's question. Yeah, so the magic here was that I told you to try dividing by x minus 1. If I hadn't told you to try dividing by x minus 1, if I hadn't suggested that, then we wouldn't know really how to get started. There's a special theorem called the rational roots theorem, which will tell you what things to try. It'll be a way of generating a list of possible factors, and then you'll check them one at a time using synthetic division. I'm going to share that theorem with you next time. But for now, I just want you practicing this because we've already covered enough here. We need to practice and get comfy. In response to the other question, I think 0 minus 1 is indeed -1. But that's not what we're saying here. We're saying that when you plug 1 in, this thing becomes 0. So I don't know if that addresses the other question or not. Okay, yeah, good. So remember, yeah, P of C is equal to 0 if and only if x minus C is a factor. So P of 1 is equal to 0 here because x minus 1 is a factor. If you plug 1 into this expression or this expression, the whole thing will become 0. I don't care what these two pieces do because they're being multiplied by this piece, which would be 0. All right, there's one more problem I'd like to solve with you guys today, and it's this issue of I give you some roots. Can you find me a polynomial that has those roots? We know that roots tell us factors, but the roots don't completely determine a polynomial. They almost determine a polynomial. So maybe let me share with you a quick fact. A polynomial with roots C1, C2 out to Cn has fully factored form right? Each one of those roots tells me a factor. So I know that x minus C1 would be a factor. All right, like this, P of x equals, I'm going to leave some space here. You'll see why in a minute. X minus C1, x minus C2, all the way out to x minus Cn. So whatever those roots are. And then over here, you have a possible constant, which I'll just call capital A. It's the lead coefficient. It's the same thing as an in the definition of the polynomial. And the c's here could be repeated, right? So maybe this is like x minus 1 times x minus 1. You could have that. But any polynomial, if you know all the roots and you're listing them with multiplicity, so like if you have a root with multiplicity 5, you would list that root 5 times like you've had to do in the homework. Then you can always write the fully factored form like this. The thing you got to remember is that there's this possible multiplicative constant out front here. And I'll talk a little bit more about that as we work through this last problem for the day. So I want to find a polynomial with roots -3, 0, 1, and 5, having coefficient of x cubed equal to -6. So here's how you do this. If I tell you the roots and I ask you for a polynomial with those roots, each one of these roots tells you a factor. So the root -3 tells me x plus 3 is a factor. The root 0 tells me x minus 0, or just x, is a factor. The root 1 tells me that x minus 1 is a factor, and the root 5 tells me that x minus 5 is a factor. Thus, p of x is some constant times x, I'll write the x out front, just looks better, times x plus 3 times x minus 1 times x minus 5. And now what I'd like to do is go into Desmos for just a minute and show you what I mean when I say there's more than one polynomial with these roots. This is a fun game to play. X minus x plus 3, 1, x minus 5, right? I'm going to add a slider for the constant a. Zoom out a little bit. Alrighty, so what you see here, let me scale my y-axis a little. Let's do just maybe 50 to 50. So what you see here is for every different number a that you can plug in, for every different lead coefficient, you get a different polynomial. Right? The graphs are different. The roots are the same. It has the same x-intercepts. But there's many different polynomials with those roots. All right, could I be looking for this one, or this one, or this one, or this one? So what we have to do in order to uniquely determine the polynomial, I have to find that constant a. And the thing that's going to let me find that constant a is this extra bit of information. They said the coefficient of x cubed has to be -6. So I'm going to multiply all this shit out. And then I'm going to look at the coefficient of x cubed and set that equal to -6. And that will uniquely determine the polynomial. Multiplying all this out is a bit of a hass, but we can do it. So I'll multiply the x times x plus 3. That gives me x squared plus 3x. And I'll multiply the x minus 1 times x minus 5. That would give me x squared minus 6x plus 5. And then I need to distribute all this stuff. So if you've never tried to distribute a binomial over a trinomial, let me show you how to do it. What we're going to do is multiply this whole thing by x squared, and then add that to what we get when we multiply this whole thing by 3x. I'll write it like this. X squared times x squared minus 6x plus 5 plus 3x times x squared minus 6x plus 5. So this is how you distribute, large things. You take each piece here and multiply it by this whole thing. So x squared times this whole thing plus 3x times this whole thing. It really is just distribution, but you have to think about it a little carefully. Now, when I get to this step, I now have to further distribute this x squared over this trinomial and this 3x over this trinomial. So I'll get from the first group x to the 4, x squared times x squared, minus x squared times 6x is minus 6x cubed. X squared times plus 5 is plus 5x squared. And then I have this plus 3x times x squared is 3x cubed. 3x times -6 is minus 18x x squared, and 3x times 5 is plus 15x. Finally, we have to combine our like terms and distribute the a. So I'll combine like terms first. There's only one x to the 4. I've got two x cubed terms, a minus 6x cubed here and a plus 3x cubed here. Those add up to minus 3x cubed. I have a plus 5x squared here and a minus 18x squared here. That's minus 13x squared. And then just the one x term, the one linear term, plus 15x. So finally, when I distribute that a, I get ax to the 4 minus 3ax cubed minus 13ax squared plus 15ax. Now we're almost done. They said this thing has to have the coefficient of x cubed be negative 6. Well, the coefficient of x cubed is negative 3a. So they told me that this should be equal to negative 6, i.e. Negative 3a equals negative 6. And then if you divide both sides there by the negative 3, you get a equals 2. So my polynomial, the polynomial that satisfies all this stuff, has these roots and this cubic coefficient would be, I'll write the factored form, p of x equals 2x, x plus 3, x minus 1, x plus 5. And this would be your answer. Problems like these, wink, hint, nudge, show up on exam 2 almost 100% of the time. I give you some roots and I ask for a polynomial with those roots. And then there will be some additional bit of information, something like this, although not necessarily this, that allows you to determine the lead coefficient. So remember, the roots don't uniquely determine the polynomial. The roots only determine the polynomial up to this multiplicative constant called the lead coefficient. And in order to know for sure which polynomial you're talking about, we have to throw in one little extra bit of information. All right, that's section 3.3, lads and ladies, dividing polynomials. There's a bunch of cool shit we can do with it. Practice it, practice it, practice it, practice it. If you don't practice this, then the next lecture is going to be kind of, and the material from here doesn't get easier, it gets harder. We got more work to do. So please, please, please get in, practice the 3.3 homework. If you need any more time with anything, you can submit an extension request in WebAssign. I cleared all of those out yesterday. I had like 50 of them. But if you need any more time with any of this stuff, you can submit an extension request. I want you to work the problems. You need to work the problems. Don't symbol lab, Mathway, whatever, fuck bullshit. Take the time to work them. I'd rather you take more time on them than cheat and not actually work them, because working the problems is how you learn the stuff. If you're stuck on anything, you can always ask me for help. Discord, Canvas, office hours. You guys know the drill at this point. Remember to review your tests. Take a look at the comments I made. There's lots of stuff there. You definitely need to learn from those. And if you have anything else you'd like to talk about, you can always reach out to me through email or Canvas message. That's it from me for today, guys. I hope you have a lovely rest of your day. And if there's anything I can do for you, again, please don't hesitate to ask for help. Take care.